Right, and now let's go on to question 8. They say we've got two identical positive, or rather point charges, X and Y, that are placed 2 millimeters apart. Point P is 3 millimeters to the right of charge Y. They say the net electric field at point P is 5.44 times 10 to the exponent 6, right, newtons per coulomb. This is to the left. Now, the fact that they told us that P is simply a point. So remember, what we're going to do is we're going to assume, we always do this, we assume that that is a positive point charge, a test charge, right? So we assume that point to be positive. Now, the net electric field at that point is to the left. So which means that we're assuming that that point charge, that positive point charge, would actually be to the left, okay? So meaning that the charges on X and Y respectively have to be negative so that they attract that, that point charge to the left, okay? Right, so now they say to us, define the electric field at a point. Remember that electric field, by definition, it is the point where electrostatic force is felt per unit charge, right? Or you can say the area where electrostatic force is felt per unit charge. Right, now they're asking, are the charges negative or positive? We've just stated this, right? We said they should be negative, and the reason for that is that they need to be able to attract that positive test charge. Right, now they say draw the resultant electric field pattern, right, for charges X and Y. Okay, so what I'm going to do there, let me just draw them over here. Okay, these are point charges, right? They are identical in charge. So I know that they are negative, by the way. So that means that our electric field will actually be in that direction. So it will be an electric field that is moving towards the center of the charges. Okay, so let me just try to do this. Okay, right, so that remember that the fields have to they must not rather cross one another, right? So I'm just trying to draw them so that they are equal or identical. Okay, so there's my charges. Okay, so it was misbehaving at first. Now please remember, because we're dealing with negative charge, we know that the field lines would be moving towards the point charge, or inside, okay, towards the center, and that would be the same also for the other point charge as well. Because these charges are equal in charge, right? So that means that the density of the lines, meaning that the number of lines that I will actually indicate there, should be the same. What you can do is just draw that asymptote for yourself there, so that you show that they are actually not going to touch each other. Right, so that's what our field line pattern would look like, okay, or our electric field pattern, okay. So they say to us, calculate the magnitude of charge X. Now, remember that you've got the electric field, right, that will be on P because of X and because of Y. So X would be attracting that point charge, so EX, right? But you'd also have EY, and I truly believe, well, not just believe, but I know EY would actually be much bigger, right? Because of the fact that the distance is actually smaller. So, which means E net would be equal to EX plus EY, right? EY. Right, now our net electric field in this case is 5.44. Right, so that's 5.44 times 10 to the raised to the exponent 6, right? And we know this is going to be kqx over. Now, if you notice the distance between x and p, that would be 2 plus that 3. So that gives us 5 millimeters, right? So that would be 5 times 10 negative 3. Note this is in millimeters, and we must square that distance. Plus, in this case, it would be also kqy, right? And the distance between y and p is 3 millimeters. So that would be divided by 3 times 10 to the negative 3 squared. Now, ladies and gents, let's just substitute. So this would be 9 times q of x, but we know that q of x is equal to qy, so I'm just going to leave it as q. So this is 9 times 10 power 9q divided by 5 times 10 minus 3 all squared, plus, again, the same thing there. That's q divided by 3 times 10 minus 3 squared. Right, now we're going to try and, so this is equal to 5.44, okay, times 10 to the exponent 6. Right, so we need to find a way in which to add those two together, right? So let's do that. So that's going to be, the first one is 9 exponent 9, okay, divided by 5 exponent negative 3 squared. Okay, so that's the first value for q, plus another 9 exponent 9 divided by, okay, so that would be 3 exponent negative 3. Okay, once again, we're going to square this, and I close that entire bracket, right? So I get 1.65 times 10 to the power 15, 1.36 rather, times 10 exponent 15 q, when I add both of them, right? And this is equal to 5.44 times 10 exponent 6. So I'm going to divide by 1.36, okay. Okay, what I do on the left, I do on the right. And what should be our value for q? So this would be, so I'm going to take that answer and divide by 5.44 exponent 6, right? And now what I'm going to do is just simply take the inverse of our answer there. Okay, and what does that give us? That gives us 4 times 10 to the negative 9 coulombs. So this is going to be 4 nanocoulombs, right? But please remember, we did say that they are negative, so that means that we're going to have that negative charge over there. Right, but we were just interested in the magnitude, so it's not necessary to put the sign. Right, now they say to us the charge on Y is now replaced with an identical, oppositely charged point charge. Okay, so they're telling us that instead of having a negative charge, now we're going to have positive. They say, how will the magnitude of the net electric field at P be affected? It will definitely decrease, right? Okay, so it will definitely decrease. And they say, give a reason rather for the answer. So notice Now, what you're going to have is that you're going to have two fields that are opposing each other, right? So it is going to decrease, okay? Right, and why is that? Because E net is now going to have EY minus EX, whereas initially they were additive. They actually, we took the sum of the two, right? Now, because the other field is now in the opposite direction, right? So the field due to Y, the field on Y will oppose, or rather, let's say, will be in the opposite, will be in the opposite direction. And so the net field, E net, will decrease. Okay, right, so that is really how we're going to answer that. Right, ladies and gents, let's go on to the next section, which is question 9. All right, I hope that was clear.